Hi, I'm Ali, and I'll be showing you how I built a complete pipeline for energy demand forecasting and grid optimization. Our electric grids are under pressure from intermittent renewables and shifting consumption patterns. My project mainly does two things. It forecasts the next 24 hours of household load and solar generation, uses a reinforcement learning agent to decide when to charge or discharge a battery to minimize grid draw. Now I'll be coming to what datasets I've used for this project. I've gotten daily temperatures and precipitation for Sharjah Airport from NOAA, and I've used UCI household power consumption data for 1 minute resolution global active power. Finally, a solar plant output from Gaggle gives us PV generation history. Together, these three feed our forecasting and simulation pipeline. Next, let's dive into our code. First of all comes our data loader.python file. This is where the raw CSVs become analysis ready time series. To begin with, we have the load data function, which basically cleans and resamples the UCI household power file into a neat hourly load curve. Second, we have the load solar data, which basically pulls in two Kaggle solar plant out data sets and stitches them together for per hour generation and sensor readings. And finally, we have the load weather data function, which basically parses through the Sharjah air station's precipitation and temperature, so everything shares the same date time index. By the end of when we run this file, we get three bundle data frames, which are basically solar, load, and weather, which are aligned for modeling. After this comes the weather forecasting code, which basically is renewable, which basically shows that renewables and demand both depend on weather. We know this as a basic fact, so we wrap a simple whole Finster exponential smoother in a class, and we use a function called predict to point out at a historical station CSV, and it spits us back a 24 hours of exogenous features that include rainfall, temperature, and similar materials for use downstream. Now, although this is not a traditional way of doing it, like you could have used Sarimax or other models, but this seemed to be way faster compared to another way of doing it. I had tried Sarimax, but it was really slow and not that fast compared to Worldminster. Now we come to our run forecaster Python file. This Python file is basically where all the main ingredients are thrown into play. First, we load and feature engineer solar and load data with Fourier terms, lags, and Rolex starts as this is the and also we use an 80-20 training split. And for this model, I've used XGBoost model, and for this, I've used tuned hyperparameters, which include the learning rate of 0.05, as I found that to be the best fit. And the evaluation metrics that I've used for this is MAE, RMSE, and R square. And for both solar and load, I've gotten R square values greater than 0.8, some reaching near 0.96, and this shows that how good fitting our model is. Now I'll be showing you my energy environment gem file. This is basically a simple gem environment which models 1 day of solar generation, household load, and a battery. At each early step, the agent sees three vector, the normalized solar output and normalized load, and the current battery state of charge. All of these are in 0 to the 1 per unit. And according to these inputs, it chooses action. And this action can either be hold, charge, or discharge, as shown here. Charging or discharging moves the battery by a small rate. and it is this small rate varies between empty and full. Now, this environment computes the net grid draw as load solar battery delta and assigns a reward that penalizes any grid import plus a small penalty for cycling the battery. And I've also included an incentive mode that rewards self consumption of solar instead. And each episode runs 24 steps, and by maximizing the cumulative reward, our reinforcement learning agent can learn when to charge or discharge, minimize to minimize the grid usage. Now I'll be showing our what we say our Streamlit front end, where everything. Sorry, I've forgotten the main reinforcement learning agent, which the training file for that. What I've done here is basically load a week of historical solar and load data, and fetched it from which fetches 24 hours exogenous weather and wraps it all into this energy environment. After this is done, what happens is I've trained a DQN agent with evaluation checkpoints. And after this, I get a safe policy that knows how to dispatch the battery to smooth a net grid draw. And the reason I chose DQN and not PPO or other agents was because this seemed to give me the best outputs compared to the others. Finally comes the Streamlit frontend, which basically ties everything up together. It runs the forecaster, steps through the reinforcement learning policy, and plots the forecasts, the battery SOC, and net grid draw. Now I'll show you the demo of how the Streamlit app looks like. As you can see here, I first plotted the solar and load forecast, and you can see how the solar forecast ranges over the day, and it peaks at midday around 12 p.m., 11 a.m., and it steadily goes down as the day ends, which is shown pretty similar to what is there in the dataset. And whereas load varies from 1 to 1.5 kilowatts and does not change much. This forecast basically informs us when we have excess renewable energy to store or when we have to draw from the grid. Now I have a battery levels and actions graph. This graph, as you can see it charge up during the peak solar usage and at that stage the action is set to be 1. It makes it hold the charge or makes it charge more, so it can be consumed. Whereas when it starts going low, you can see that it's being told to discharge the battery. And now I'll explain the net grid draw and reward, what these graphs are showing. They basically show the reinforcement learning agent's total reward over time, where high is better. Because our base reward starts from negative absolute grid, this curve goes downward and not upward. And you can see that the flatter sections indicate hours where the battery helped shave the peak successfully. And I've also given a raw simulation table for reference, shows the action and the reward which the battery is being given. So you can see exactly why the agent was rewarded or penalized. And to determine the reward shaping, I've allowed the option to change the cycle penalty and to use an incentive or not, which I've already explained in the gym environment code. So this is pretty much it of how I've done my energy and grid energy forecasting and grid optimization. Mainly where I found The difficulty was determining which models to use for training. When I'd started with SciMax, it was taking way too long and not giving me decent outputs. I was uh, um, getting mean errors in thousands for solar, and that took a while to figure out and how to fix, and also how to properly reward the reinforcement learning agent was also a challenge to figure out for me. So this is around it for the project. Thank you very much for watching.